The purpose of this lesson is to show you how to write an equilibrium constant if you have a balanced chemical equation. Now we're going to start with just a generic equation where we have reactants A and B becoming products C and D. We're also going to write our first equilibrium constant based on knowing how much reactant and product we have in terms of molarity of our reactants and products. The other thing that I would mention is that we write these equilibrium constants based on amounts when the reaction has had time to go to equilibrium and we're sure that we're at an equilibrium state. So equilibrium constants are represented by capital K, and if we're writing them based on concentration amounts or molarity amounts, we'll just write a lowercase c. So that's equilibrium constant based on molarity concentration. Now an equilibrium constant is just a ratio of the amount of products over the amount of reactants. So we would just write, in this case, concentration, molarity concentration of C. Now we raise the concentration based on the coefficient in front of that substance in the balanced chemical equation. So there you go. We have C and D as the products. We raise the C to the C. We raise the D to the coefficient in front of the D. And we divide that by the amount of reactants that we have. Like this. Now, one other thing that I would note, there's a reason for this, a reason that I won't take time to explain right now, but we don't include the units when we write equilibrium constants. We have the products over the reactants. When we get done, we'll have a number for our equilibrium constant, but we will essentially, at this point, ignore the units. So it will just be a number based on how much reactant and product there are when you've reached equilibrium. Now, we could also write equilibrium constants in terms of pressures. So you could have partial pressures. If you have a gas equilibrium, you have the pressures of your gases that are products and gases of reactants, and we really would take the same approach. We'll write the equilibrium constant with respect to pressure, but if our reaction is shown above, then we would take the partial pressure of C, that's capital C raised to the little c, times the partial pressure of the D in the mixture raised to its coefficient. Divide that by the product of partial pressure of A, that's an A, and the partial pressure of B. Again, if we're in terms of atmosphere pressure, we still wouldn't include the units when we write our equilibrium constant. Now, again, writing the equilibrium constant is pretty basic. Once you see the pattern, anybody can write equilibrium constant. Let's go and do that with an actual chemical reaction. So here's a basic chemical reaction. We've got hydrogen iodine reacting to make hydrogen iodide. The equilibrium constant for this, and we'll do it based on concentration, would just be written, like we saw on the previous page, as the concentration of HI at equilibrium, and we'll square that, again, because the coefficient is 2. We'll divide that by the concentration of H2 and the concentration of I2, like that. Now, I have written just below this equation some experimental data. Now the scenario is, you can see the equation again, written here, and we have initial concentrations for the hydrogen and the iodine shown, and in this case we don't start with any of the product in the mixture. If we wait long enough for this system to come to equilibrium, if we start with 0.1 molar of each one of the reactants, we'll end up, after time, with 0.156 molar HI, and both of our reactants will be 0.0222. Now, can we calculate an equilibrium constant from this data? What will we do? We'll take the concentration, that's 0.156, didn't draw that real well, but the concentration of the HI, we'll square it, we'll divide that by the concentration of the H2, and I could just square it because they're the same, but also the concentration of the I2, and we can just plug that in our calculator and we will have calculated our first equilibrium constant. I believe if you plug that in, if you do it, what you'll end up with is 49.4. Now, what I'd like you to do, see, we have a few different scenarios, different situations where we started with, instead of reactants or things on the left-hand side, we started with product. Now, if it's an equilibrium, what's going to happen? Remember, forward and reverse reactions both take place. In this case, since you didn't start with any of the left-hand side substances, or what we typically used to call reactants, you'll drop the concentration of the product as you make more reactants. Now, the third scenario, we start with some product, a little bit of reactant, but none of the hydrogen. Again, we'll come to a certain equilibrium point. What I want you to do is calculate equilibrium constants for this set of circumstances and this set of circumstances and see what you come out with. Hopefully, if equilibrium constants are really constant, you'll get a number similar to what we got for the first set of data. Okay, give that a try and perhaps even go work some homework problems. Now that you've had some experience writing equilibrium constants, seeing how that's done, I want you to take a minute and write the equilibrium constant for this chemical equation. Now, the best thing for you to do is to pause the video and to do this on your own before I show you what I would do. Okay, now hopefully you have an equilibrium constant written. Now I'm going to write the equilibrium constant. You know that I'm simply going to write concentration of products over reactants. There's my products. All the coefficients are 1. That makes it easy. So my exponents in my equilibrium constant expression are also all 1. And believe it or not, there's the right answer. In equilibrium constant expressions, we don't include liquids or solids. The reason that we would say that we do not do that is that the activity for liquids and solids are 1. Now, I don't expect you to completely understand what I mean by activity, but the simplest way to think about this is that if you have a liquid, you can't really change the concentration of that liquid. Or if you have a solid, a pure solid, its concentration doesn't change. So as long as you have a solid or liquid in the equilibrium, it doesn't matter how much is there. If we have a solid or a liquid in a chemical equation and we're writing an equilibrium constant for that equation, we do not include the solid or the liquid in the equilibrium constant expression.